Alright, hi everyone and welcome back to the channel. I hope all of you are doing great. So in today's video, we are going to be discussing the solutions to Facebook or Meta Hacker Cup 2023 round 1. And talking about the round, I think it was a pretty decent round. I think all the problems except the last one were solvable with some amount of effort. Okay, so all in all, I would say that the round was pretty good. It was a well balanced round. The difficulty also increased linearly. So yeah, all in all, a pretty good round. The only problem was that there were quite a lot of server issues, and I mean that affected me personally because I thought that I would be competing seriously, but for the first 1 hour the servers weren't working at all for me. So then I just decided to just do the bare minimum, and the bare minimum to qualify for round 2, and I was also feeling quite sleepy. So yeah, I didn't compete seriously after that. I only did the first 2 or 3 problems, and then I stopped competing. But overall, I think the quality of the problems wasn't bad at all. So yeah, that's about the round. I think we'll be discussing the solutions to problems from A to D. So yeah, without any further ado, let's start with the solution to problem A. Okay. So in this problem, basically Santa Claus Lane is a home for n elves, and the ayat of whom lives at xi meters from the start of the lane. Okay, so there are basically n elves who, and the ayat elves lives at position xi. And as Santa's little helper, you're tasked to assign elves to work on toys for little boys and girls. Okay, so specifically, what you need to do is you must assign each elf to work on some toy. So that at least 2 toys get worked on. So not all the elves can work on the same toy, and also no elf works on a toy alone. So that means for every toy there are at least 2 elves that are assigned to that toy, and the number of toys itself should also be at least 2. Okay. Now, all the elves working on the same toy, they will meet at some point, and they will meet at such a point which minimizes the farthest distance that any of them would have to walk. So formally, if the elves are assigned to like the elves which are assigned to a given toy, they lie at positions x1, x2 up till so on and so forth. Then they will meet at a point P such that the maximum value of absolute value of x1 minus P, x2 minus P, so on and so forth is as small as possible. Okay. Now, what we need to do is basically, among all valid assignments of elves to toys, what is the farthest that Santa would need to walk to visit all the meeting points? And the constraints are that Santa may start and end from anywhere. Okay, but whatever he does, he will always try to walk as little a distance as possible after seeing your assignments. Okay, so our job is to make Santa walk as much as possible, whereas Santa will try to minimize the total distance that he covers. Okay, so the problem statement might be a bit long and complicated, but indeed the problem isn't that hard at all. Okay, so yeah, that's the problem statement. I hope it is clear. And yeah, let's go ahead and look at the solution now. Okay. Right. So yeah, the first observation that also is pretty trivial. So the first observation that also is pretty trivial is that if we assign some elves to a toy, then they will actually meet at the midpoint of the leftmost and the rightmost elf. Okay. So what I'm trying to say is, so let's say that we assign all of these elves to work on the same toy. Let's call the index of these elves as x1, x2, x3, x4, and x5. Then what happens is that they will look at the midpoint of position x1. So they will look at x of x1, and they will look at x of x5. Okay, and they will actually meet at the midpoint of these two values. Okay, so they'll meet at the midpoint of x of x1 and x of x5, and the reason for that is pretty simple because let's say that this is the midpoint. So if they decide to meet at any point other than this, let's say they decide to meet at a point which is to the left of this midpoint, then obviously the elf x5 would have to travel a larger distance, and for the similar reason, if we decide to meet at a point which is to the right of this midpoint, then the elf x1 would have to travel a larger distance, right? And so we need to minimize the maximum distance traveled, and that's the reason that the optimal choice for the meeting point of all of these elves is going to be the midpoint of x of x1 and x of x5, which is nothing but x of x1 plus x of x5 by 2. Okay. Right, and now the second observation in this problem is, let's say that we are making in total k toys, and the meeting point of all of these k toys are now x1, x2 up till xk. Okay. Now Santa obviously wants to minimize his distance traveled, so obviously what he's going to do is he'll start from x1 and he'll just travel till xk, or he can also do the reverse. He can start from xk and then he can just travel till x1, because this is his obvious choice since he needs to cover all the points exactly once. So he will start from one extreme point and then go to the other extreme point, right? So our job in this problem is nothing but to maximize the total distance that Santa travels. And so what we need to do is we need to maximize the distance between these points x1 and xk. Okay, and well, this is it, right? The solution is actually staring us in the eyes, so the solution is pretty simple. So what we can do is we need to make sure that x1 is as left as possible and xk is as right as possible. And the optimal way to do that would be to choose the first two elves to work on one toy, to choose the last two elves to work on some toy, and to choose all the middle elves to work on some other toy. And doing this will make sure that x1 is as left as possible, because obviously we need at least two elves for each toy. So why not choose the first two elves, and that will make sure that x1 would be somewhere here. And similarly, we need to make sure that xk is as right as possible. So we are taking k equals to 3 here. And so the optimal thing to do would be to take the last two elves and make them work on some other toy. And so xk will be somewhere here. So doing this will actually maximize the distance that Santa will have to travel. And that's going to be our solution. Okay. Well, not really. The caveat here is that there might as well be a possibility that the number of toys in between, the number of elves in between is actually equal to 1. And now this is actually not possible, because this is not allowed, since each toy has to be worked upon by more than one else, strictly more than one else. And so n is equal to 5 is actually a corner case that we'll need to handle separately. Okay, so if n is equal to 5, what we need to do is basically this one elf will actually have to work on either the left toy or the right toy, because it can't be alone. So we can just try out these two cases. So one case would be that the first toy is being worked upon by the first three elves, and the second toy is being worked upon by the last two elves. And the second case would be that the first toy is worked upon by the first two elves, and the second toy is worked upon by the last three elves. So we can just try out these possibilities, both of these possibilities, and then we can simply take the maximum one, the one which maximizes the distance that Santa will have to travel. Okay, so yeah, that's pretty much the solution of problem A. Pretty decent. I think I will give it around 1000 difficulty on Codeforces. So let's just quickly look at the solution. Solution is pretty simple. So we simply take in the input, we sort the array, and then if n is not equal to 5, our solution is very simple. So L would be a1 plus a2 by 2, R would be an minus 1 plus an by 2, and the answer is going to be R minus L. Okay. Otherwise, if n is equal to 5, we'll just try out two possibilities. In one possibility, we'll give the first, second, and third toys to the first, second, and third elves to the first toy, and the last two elves to the last toy. Okay. And in the second possibility, we'll give the first two elves to the first toy and the last three elves to the last toy. And we'll simply take the maximum of these two possibilities, and that's going to be our answer. Okay. Right. So yeah, that's the solution of problem A of Hackercup round 1. And let's now quickly move on to problem B, specifically problem B1. So we'll be discussing B1 and B2 pretty much together. Yeah, so let's see. So in this problem, we are given a positive integer p, and we need to find out an array of at most 100 positive integers which have a sum equal to exactly 41 and a product equal to exactly p. Right, so such a simple problem, right? So we simply need to find out an array with a given sum and a given product, or we need to output -1 if such an array doesn't exist, right? Right, so the difference between B1 and B2 is that in B2 we need to output such an array with the minimal possible size, and in B1 we can output any such array. Okay, so let's try and solve both of these problems together, and then we'll look at the codes of both of these problems separately. Okay, right, so let's go for B1. And let's try to see how we can solve this problem. Okay. So problem B1, how to solve this. So what we need is, if you notice the constraints, the number n is not infinitely large, so it is bounded by 10 raised to the power 9, and that is something that we can use to our advantage, right? Cool. So if n is up till 10 raised to the power 9, it is allowed for us to factorize n. Okay, so we can factorize n. Reason for that is factorization works in O of square root of n. So it is allowed for us to factorize n, and it is also allowed for us to prime factorize n. Okay. because both of these algorithms work in order of square root of n time, and since n is up till 10 raised to the power 9, even if we multiply it by the number of test cases, capital T times square root of n is still pretty small. Okay, cool. So yeah, so let's say we now factorize this number n, and we essentially try to prime factorize this number, and we get its prime factorization, which looks something like this. Okay, p1 raised to the power k1, p2 raised to the power k2, up till pm raised to the power km, something like this. So this is the prime factorization of the number n. Now my claim is that to solve the problem p1, to solve the problem b1, what you can do is your final array is actually going to look something like this. Okay, it will contain p1 k1 times. Okay, then it will contain p2 k2 times, then it will contain p3 k3 times. Okay, so this is k1 times, this is k2 times, this is k3 times, so on and so forth. Okay, so this is how your solution is going to look, and this is my claim that the claim is that even if we try to do this, the length of our array will not exceed 100. So we will never exceed 100. Okay, and how about making the sum equal to 41? Well, if the sum is not equal to 41, then we can simply insert more ones, and inserting ones will only increase the size of the array, and it won't affect the product of all the elements at all. And right now we know that the product of all the elements is equal to n, and inserting ones will not change the product, but it will indeed change the number of ones, and we'll keep doing this until and unless we get a sum exactly equal to 41. Now why is this true? Also, a condition that this should satisfy is that all the prime numbers which are prime factors should be less than 41. Okay, should be less than 41, and summation of pi, summation pk times. Okay, so essentially what we'll do is, for I is equal to 1 to m, pi times ki, this summation should also be less than equal to 41. Okay, so this is actually a more strict condition that the prime factors should satisfy. Now why is this true? Why is this true? So my claim is that if we are not inserting any ones, the sum that we'll have, it will be less than or equal to 41. It should be less than or equal to 41 for any answer to exist. And the reason is that if we have such an arrangement as our answer, then it will actually be an arrangement with the minimum sum. Okay, so this arrangement will actually give us the minimum sum. Okay, minimum sum. Okay, now why is it giving us the minimum sum? Well, that is again very simple. So our arrangement is essentially using just one prime factor in one number, and that prime factor is also being raised to the power 1 only. Okay, so my claim is that if we use more than one prime factors, and if we combine some elements and combine them into one, then we'll have a greater sum for sure. So let's say we have a prime number p1 and a prime number p2. So right now both of these elements are separate. Okay, but if we try to combine these elements, we'll get p1 into p2. Okay, so the sum here was p1 plus p2, and the sum here is p1 times p2, and it is very obvious that p1 plus p2 will always be less than or equal to p1 p2, because sum of two numbers is always less than or equal to their product. Very natural, right? And like we know that all of these numbers are greater than 1, and this fact is true for all the numbers greater than 1. So that means if we just take out all the prime numbers separately and we just use them, then we are essentially getting an arrangement which has the minimal possible sum, and obviously it will never exceed 100. Well, the number of prime factors obviously cannot exceed 100, because even if all the prime factors are 2, the number 10 raised to the power 9 is around 2 raised to the power 30. So even if we take very small prime factors, there will be at most 30 such numbers. So we can safely say that the size of this array will not be more than 30. Okay, so yeah, the size will not exceed 30, or let's say 32 or 33, something like that. And obviously we look at the sum. So if the sum of these elements is greater than 41, then an answer doesn't exist. If the sum is less than 41, then we can simply append ones to this array until and unless the sum becomes equal to 41. Okay, right, so that's the solution to problem b1. Let's just have a look at the code, and then we'll see how we can extend this solution to take care of b2. Okay, cool. So what we are doing is, the first thing is that we'll generate a prime factorization of the number n. So this is a standard way using which you can prime factorize a number in O of square root of n time, and as and when we get prime factors, we can simply append them to our answer. Okay, and then we'll find the sum of all the elements in our answer. If the sum exceeds 41, then we can simply output -1. Otherwise, while the sum is less than 41, we can keep appending 1 to our answer and increasing our sum. Okay. And once that is done, we can be sure that we now have an answer ready. So we'll just output the size of the answer and then we'll output the entire answer itself. Right. Cool. So that's the solution to problem B1. Now let's just go back to this problem and look at problem B2. So in B2, the problem statement is pretty much the same, but the only difference here is that we also have to print this answer with the fewest number of elements. Okay, so we have to make sure that our answer contains the fewest number of elements. And if there are multiple answers with the fewest number of elements, then we can print any one of them, right? So yeah. Now how to solve this problem? So it might, the solution that I'll describe might occur to you as a bit hacky, but at the end of the day, this is competitive programming, and you have to try out various stuffs while you are giving a contest. So even if anything is not striking to you, what you should do is you should just keep doing something. You should try to write some kind of a brute force, and you should do things like this. You should just play around with the data that you have, and that is the only way in which you can solve problems for which you are completely blank. And the same was the case for me when I was trying to solve this problem. So what I did was I tried to write various brute forces, and the thing that I utilized was that the sum of numbers cannot exceed 41. Okay. So yeah, we'll use this fact and we'll actually try to write a brute force, and surprisingly we'll see that this brute force actually works within the time limit. So what we are going to do is we are going to generate all the partitions which sum up to 41. Okay, generate all partitions which sum up to 41. And what you will realize is the number of such partitions is actually not a very big number. Okay, so first of all, let's understand what exactly is a partition. A partition is nothing but a subset of numbers such that the sum of these numbers is actually equal to 41. Okay. So here I am assuming that if we have a subset which says 20, 21 and a subset which says 21, 20, then they are exactly the same because we are dealing with sets. Okay. So in sets, order doesn't matter, right? So these are unordered subsets. Okay. So yeah, that is what a partition is called. So it's just a set of numbers such that the sum of this set is equal to 41. Okay. So yeah, what I tried to do was, when I was trying to solve this problem, I simply tried to generate all the partitions. So first thing which I did was I tried to generate literally all the combinations. Okay. So by combinations, what I mean is 1, 2 and 2, 1 are not the same thing. Okay. So in that, when I tried to write the code for that, then that was definitely not working within the time limit. And so I tried to optimize it a little bit, and I tried to make sure that we are not visiting the same subset multiple times, and it actually worked. Okay, so when I wrote the code, it was taking around 5,000 iterations. Okay, so by iterations I mean that there were around 5,000 such partitions. Okay. Yeah, so if you just write a brute force to generate all these partitions, you'll realize that the number of partitions which actually sum up to 41 are not very huge. Okay, so the solution to this problem is you actually generate all the partitions which sum up to the number 41. Okay, so you do this in a pre-computation. Okay, so you pre-compute this. So you will pre-compute this. Okay, and then you will take in the input. Okay, so then you start taking in the input, you take in the number p as an input. Then what you will do is you'll simply iterate over all of these 5,000 permutations, and you'll simply find the product of each of these partitions, and you'll only be interested in those partitions whose product is exactly equal to p, and then you can simply take that partition which has a product equal to p and has a minimum size. Okay, so that's all that you need to do. Cool. So I hope this is clear. Let's just have a look at the code to see how exactly we can generate such partitions. So generating partitions is actually pretty simple. We can do this using recursion. Okay, so we can do this using recursion. Right. So what my recursive function is doing is it is taking in a vector which denotes the current partition that we have. It is taking in the current sum of elements in the partition, and it is also taking into account the last element that we used. Okay. And what I'm doing is I'm maintaining an invariant that all the subsets that I generate, they will always be in decreasing order. Okay, so if I'm making sure that they are in non-increasing order, then that means that we are never visiting a same subset more than once. Okay, because any subset has one specific order, right? So if we've reached the sum of 41, then we'll push the vector into our all subsets vector of vectors, and then we'll return. Otherwise, we'll simply iterate over the elements that we'll push back next. So this iteration will only be done from 1 to the last element. And so if sum plus I is greater than 41, then we'll simply return. Otherwise, we'll backtrack. Okay, so we'll first push I into our vector, we'll increase sum by I, and then we'll call the recursive function with the required parameters, and then we'll backtrack. Okay, so we'll remove the element I that we inserted into our vector, and we'll also decrease our sum by I. Okay, so this is how we actually generate all the partitions with sum up to 41. And once we've done that, we take the input and then we iterate over all of these subsets. We find the product of each subset, and if the product is equal to n, we check if its size is actually less than the minimum size of a subset whose product is equal to n that we found previously. And if that's the case, then we'll update the minimum size, and then we'll also update the answer. Okay, and if we don't find any vector whose product is p, then the answer would be -1. Otherwise, we'll just output the vector that we just found. Okay, so yeah, this is the solution to problem B. I hope I was able to explain it at the best of my capacity. Cool. So yeah, that's problem B, B1 and B2. Let's now look at problems C1 and C2. Okay. Alright, so in this problem, there is a puzzle which consists of n buttons in a row, numbered from 1 to n. So the initial state of the button I is white if Si equal to 1, or it is black if Si is equal to 0. So essentially we are given a binary string in the input. Now pressing a button K toggles the state of itself as well as every kth button. Okay, so if we press a button equal to K, it will toggle the state of K, 2K, 3K, so on and so forth, all such buttons. Now we need to, so your friend challenges you to return the puzzle to him with all the buttons in black. Okay, so we need to convert all the indices in our binary string to 0. And what we have is we also have to process Q queries. And in each query, we are essentially just pressing the button BI. So in the ith query, we are pressing the button BI. Okay. Cool. Now, what we need to do in the problem C1 is, after all the buttons have been pressed, so after all the Q queries have been processed, we just want to find out the minimum number of extra button presses which will be required to make all the buttons black. Okay, so the minimum number of extra operations that we need to do so that the entire string becomes equal to zeros. Okay. Right. So that's the problem. So problem C1 is actually pretty straightforward. So we'll actually first find out the solution to C1, and then again we'll build up from there to solve problem C2. Okay, so let's look at C1. So the first thing that we need to do is we need to somehow process these queries. Okay, process these queries. Now processing queries is also not trivial, because what if we always press button number 1? So if we are always pressing button number 1 and we try to naively process all the queries, then each query will take n operations, and there are q queries, so we'll have to do q into n operations just to process the queries, and both q and n are very large, and that will definitely not work in the 6-minute time limit that we have in Hackercup, right? But an observation that we can make is that order is irrelevant here. Okay, order doesn't matter. So the order in which we process the queries doesn't matter, because at the end of the day, what matters is the number of times we pressed any button. It doesn't matter in which order we are pressing buttons, because finally we have to process all the queries and we have to look at the final string. It doesn't matter what the string was in the intermediate stages. So all that matters is the number of times we pressed each button. Okay, and so again, another observation. So this is the first observation, and if we look at the second observation, so if we press a button twice, pressing a button twice will cancel the effect of the first press. Okay, now again, this is also a very obvious thing, because if we press a button I, then we are essentially toggling the state of I, 2I, 3I, and so on. And if we just press the button again, then we are toggling it back to what it was before, right? So all that matters finally is the parity of the number of times. So all that matters is the parity of the number of times we are pressing each button. Okay, parity of the number of times we are pressing each button. So if we are pressing a button odd number of times, then that means it is equivalent to saying that we are pressing this button exactly once. And if we are pressing a button 0 number of times, it is equivalent way of saying that we are not pressing this button at all. Okay, so what we can do is we can process these queries offline. We can first take the count of the number of times we are pressing each button, and now we only need to process the queries for those buttons for which we are pressing them an odd number of times, and we also need to we only need to make sure that we handle every button exactly once, right? So if a button is being pressed an odd number of times, we can say that it is being used exactly once, because only parity matters, right? Cool. So that means what we'll do is we can simply iterate from 1 to n. We can check the parity of the number of times we are pressing this button, and if it is odd, then we can just iterate over all the multiples of that number, including itself, and we can toggle its state. Okay, and this can very easily be done using a sieve. Okay, so we'll first iterate for I from 1 to n, and if the number of times the button I was pressed is odd, then we'll iterate for j from I, and we'll say that j is less than equal to n and j plus equal to I, the same way that we do in a sieve. So we can use a sieve, and then we can just process the queries, and using sieve we'll be able to process all the button presses. And once we've done that, we now have the final string ready for us, and we just want to find out the answer for this final string, at least for the purposes of problem C1. Now how do we do that? So finding the answer. So the first part was processing queries, and the second part is finding the answers. Well, it turns out that finding the answer itself is also not very hard at all. So again, we can just greedily do this. So we can find this answer greedily. And the thing is that if we look at the first index, okay, so if the first index is itself equal to 1, then we don't really have a choice. We will have to press the button 1, and we don't really have a choice because the button 1 is influenced by only itself and nothing else, right? So if s of 0 is equal to 1, then we have to press the button, okay? So then we have to press the button 0, okay? And similarly, so we'll have to press the button 1 because the string might be 0 indexed, but in the problem it is 1 based indexing, right? So if so let's just assume that the string is also 1 indexed, okay? So if s of 1 is equal to 1, then we have to press the button 1, okay? And then again, if we look at s of 2, if it is equal to 1 now, then that means that we have to press it. We don't really have a choice because we were forced to press button number 1, and that decision is final. And now we are independently looking at the button number 2 at the second index, and if its color is also equal to white, then we will have to press it, and if its color is equal to black, then we can simply ignore it, okay? And so on and so forth. We can just carry forward with this greedy algorithm. We can just check whether the color of the ith button is currently white or black. If it is equal to white, then we will just press the button, and again we'll be applying the concept of sieve. So pressing a button means that you need to iterate over all the multiples of that button, of that number, and then you need to toggle the state of that button as well, okay? Right, so yeah, this is how the solution works. Using sieve and this greedy algorithm, you can just find out the number of operations. Let's just quickly have a look at the code. Right, so the first part here is processing queries. Right, so here we are processing the queries. So processing queries is pretty simple. So first of all, you find out the parity of the number of times you are changing an index x. So if that parity is actually equal to odd, then you iterate over all the multiples of I, and you just toggle the state of that button, okay, of that index, and then you'll just find out the answer, okay? So this is finding the answer. So you just have to write 2 sieves, and in this sieve again, you'll iterate from 1 to n. You'll see whether this index currently has a 1 or not. If it does have a 1, then you'll increment your answer by 1, and you'll iterate from I to n and j plus equal to I, the standard sieve loop, and you'll also toggle the state of that particular index, okay? So this is the greedy way using which you can solve this problem, right? Cool. So now let's jump our focus to problem C2, okay? So the difference between C1 and C2 here is that in C2, apart from just finding the answer after processing all the queries, you actually have to process each query, and then you have to find out the answer for that query. and then you need to finally find out the sum of all such answers. Okay, so that means after each query you should know the answer. Okay, and the answer is the minimum number of operations required to turn all the buttons black. You need to find this value after each query, and then you need to sum up all the answers. Right, so how do we solve problem C2? Well, for C2 we will pretty much use sieve as well. So we'll be using sieve the same way we used in problem C1, but we'll just make one extra operation, and that will make our life very, very easy. Okay, and that observation, let's try to look at that observation. So that observation is that adjacent answers will not differ by more than 1. Okay, adjacent answers will not differ by more than 1. So what I mean by this is that if we have the answer for a particular state of the string, and now we are pressing a button in the string, then we only need to take care of just one button, and pressing or not pressing that button will be the only change that will be happening. Okay, so that's the observation that I'm trying to make. Okay, so for example, let me try to understand this in a much better way. Let me try to explain this in a better way. So what I mean by this is, let's say we already had the answer. Okay, so let's say there was a subset of buttons that we were pressing in the string, and now we changed one button. Okay, so we changed the index, we actually pushed one button. So that's how a query works. So in a query you push a button. Okay, so what I'm saying is, when we push a button, there will be only one out of these, maybe out of these or out of the ones which were not being pressed, it doesn't matter. So it can be any one of those. So there will be exactly one button whose state will be changed. Okay, so by state I mean whether it is being pushed or not. Okay, so if it was not being pushed previously, then it might be pushed in this step, in this, after this query, and if it was pushed previously, then it may not be pushed after this query. Okay, so only the state of, for example, let's say this button will be changed after processing our query. So that's the observation that I'm trying to make. And adding on to this observation, that button is actually going to be the button that we are pressing in the query. Okay, so if we are pressing a button in the query, in the final answer, only the state of that button may or may not change. The state of other buttons will definitely not change. So that's the observation that I'm trying to make. And let's see the reason. Okay, so let's say that we press the button number K. So if we press button number K, we are essentially toggling the states of button numbers K, 2K, 3K, 4K, so on and so forth. Okay, so yeah, so let's make two cases. So case one is that previously the button K was not being pushed. Okay, so in the minimum number of operations that we were finding out before processing this query, this button K was not being pushed in the minimum number of operations. Okay, so K was not pushed before. Okay, okay, so if K was not pushed before, then that means that when we iterated from 1 to K and we reached K, then K was already black, because that's the only way our greedy algorithm did not push this button. Okay, so it was already black. But now, since we are toggling this button, this button has now become white, because we know that if it was not pushed previously, then it was a black button. But now it has been pushed once. Okay, so if it has been pushed once, then that means that so we are just toggling the states of K, 2K, 3K, and so on and so forth. So we'll again start our iteration in the greedy algorithm from 1 to n, and when we reach K, this time we can be sure that the button K would be equal to white, because we haven't changed the state of any buttons in this prefix from 1 to K minus 1. So everything stays the same there, but the only difference is that now we have toggled the button K. So we have done the operation on button K, and we have toggled the states of K, 2K, 3K, and so on and so forth. So now we are sure that the button K is actually a white button, and we have to push it. Okay, so now we have to push the button K. So we have to push K. Which means answer plus plus. Okay, right, so the answer is actually one more than the previous answer, but we also have to prove that we are not changing anything with these buttons 2K, 3K, 4K, so on and so forth. Okay, obviously all of these buttons in between stay the same, right? Because nothing is changing on these buttons, everything is exactly the same. these buttons in between are impacted by what we do with their factors, but we can be sure that their factors do not include k, 2k, 3k and 4k, because all the numbers which have k as a factor are itself k, 2k, 3k and 4k. So all the numbers in between, their state remains exactly the same. So if they were pushed before, they will now also be pushed. If they were not pushed before, they will now also not be pushed. But I will also prove this, that we will not be changing the states of these buttons as well. Okay, so we'll only change the state of button k. So we've already proved that we have to change the state of k. So if it was not pushed before, then now it will definitely be white, so it will have to be pushed. So let's see why exactly the state of 2k may not be changed, and the same proof will hold for 3k, 4k and all the other buttons which are multiples of k. Okay, so let's see why that is true. So in this case, k was not pushed before. So if k was not pushed before, then that means that k was not impacting 2k at all before. Okay, so k was not impacting the node 2k at all, right? So when we in the previous before processing this query, when we reached that node number k, when we reached that button number k, we were not pushing that button, and so k was not actually impacting anything with 2k. Okay, right, but now it is impacting it, right? So now it is impacting 2k. So when we iterate from 1 and we reach 2k and we process this k, then that has toggled the node that has toggled the button 2k once. Okay, so we've toggled it once, but we are also toggling all the buttons k, 2k, 3k ourselves, right? So the operation being done on k is toggling all of these buttons once, right? So in total we are toggling it twice. And if we are toggling a button twice, then that means that its state is actually unchanged. So we started with this observation that if we toggle a button twice, then it will actually come back to its initial state, right? So 0 to 1, 1 to 0, or 1 to 0, 0 to 1. So that means that we are toggling this button twice, and if we are toggling it twice, then that means it is back to its original state. So if it was pushed previously, it will be pushed now, and if it was not pushed previously, it will not be pushed now as well, right? So this way I have proved that we won't be pushing button 2k, and similarly we can also prove that we won't be pushing 3k, 4k, so on and so forth, because only k is impacting all of these nodes. 2k is not impacting them, because 2k, the state of 2k is the same as it was before. Okay, and the exact same proof can be applied to all of these nodes 3k, 4k as well. And case 2 is very similar. So case 2 is when k was actually pushed before. So k was pushed before. When I say that k was pushed before, I mean that in the greedy algorithm that we are trying to do, we were actually pushing button number k. Okay, alright. So now if k was pushed before, then that means that previously k was actually a white button and we were pushing it to convert it to a black button. But now since we are toggling all the buttons from k, 2k, 3k, now that means that k is already a black button and we need not push button k. Okay, so previously this button k was being pushed, so that means its impact was there on 2k. So we were toggling 2k when we were at k, because we were pushing the button at k, and if we were pushing the button at k, we were also toggling 2k. But now we are not doing that toggle. Okay, so it's a reverse toggle, and a reverse toggle is actually the same as a toggle. So again we can say that it is being toggled once, because previously when we reached that button number k, we were doing an operation there, and so we were changing the state of 2k as well. But now we are not doing that. So that means that is very similar to toggling it once, not toggling it like we were toggling it before, but we are not toggling it now. So that means it's a single toggle. And then obviously we are separately toggling it as well, the same way we toggled it here. Okay, so we are separately toggling k, 2k, 3k and 4k. So again we can say that we toggled it twice. And again, toggling twice means that the state of the button is unchanged. So if the state is unchanged, we can use a very similar argument that we made in case 1, that the state of every button other than k will stay the same. And that's it. That's the entire solution. So we can simply maintain a Boolean variable for each button, which denotes whether we are toggling it or not, like whether we are pushing it or not. Okay, and if in a query we are changing button k, we are pressing button k, we will just check whether it was previously toggled or not. If it was previously toggled, then we'll not toggle it now and we'll do answer minus minus. If it was not previously toggled, then we will toggle it now, and so we'll say answer plus plus. Okay, that's it. So that's the solution. It's that simple. Okay, so let's just have a look at the code, and that will clarify things a lot. So yeah, now before processing any query, we'll use the same algorithm that we did in problem C1 to find the initial answer using our sieve. Okay, so this is the exact same algorithm. And now what we'll do is we'll just read in the queries and we'll create a boolean vector change. Okay, so if we are actually doing the operation from the button I, change of I will be true. Otherwise change of I will be false. Okay, and then we'll just take in all the queries, we'll read in the number x. So if change of x is true, then now change of x will become false and current answer will decrease by 1. Otherwise change of x becomes true and current answer increases by 1. Okay, and then we'll do the final answer plus equal to current answer, because we need to find the sum of all the answers, and we can output the final answer. Okay, so yeah, that's the solution to problem C1 and C2 combined. I hope I was able to explain it. Cool. So let's now jump to problem D, which is going to be the last problem that we discussed today, and let's see how we can solve this problem. So the problem statement is very simple to understand. So in this problem, you are given n numbers. All the numbers are less than 10 raised to the power 9 plus 7 initially. What you need to do is you need to process q range queries, and in each range query, you need to actually multiply the value of all the elements from li to ri by 10 raised to the power 9 plus 6. Okay, and you also have to take its remainder modulo 10 raised to the power 9 plus 7. And after processing every query, you also need to tell the maximum number which is present in the array. Okay, so after taking the remainder from 10 raised to the power 9 plus 7, you also need to tell the maximum number which is present in the array. Essentially, you need to find the index of the maximum number which is present, and if there are multiple indices which have the same value, which is the maximum value, then you need to output the leftmost such index. Okay, so that's the problem statement. So it seems very simple that we only need to multiply numbers, and then we need to multiply numbers and maintain the maximum, but it actually isn't that simple, and let's understand why. Okay, so it is not equivalent to range multiply and range add queries, and the reason for that is very simple. It's just that we are also taking a remainder, right? So it's not simple multiplication. We also need to take remainder 10 raised to the power 9 plus 7. So that means if there was an element which was maximum before, and now we take its remainder modulo 10 raised to the power 9 plus 7, that element might not remain the new maximum. Okay, so a new element might now become the maximum. And so that's why it is different from the simple range multiply and range maximum queries. Okay, so range multiply is the update and range max is the query. Okay, of course we will be using segment trees here, because this is a straightforward range query problem. So we will definitely be using a segment tree here, and the segment tree will be involving lazy propagation, because we need to do range updates, but we will just have to slightly change the implementation of the segment tree. Also, first of all, if you guys are not yet familiar with my template of generic all-purpose segment tree, then I will just link to the video explaining that template in the description, and in the description of that video you can also find the link to my template, and in that video itself you can find my explanation to the template. So it's a very easy to understand template, and all you need to do is you need to fulfill the combine functions, the apply update functions. So the combine function, apply update function, and the combine update functions. Okay, so these are the three functions that you need to change always. Okay, so yeah, if you are not yet familiar with my generic all-purpose segment tree template, then do have a look, because it will make your life much easier as a segment tree coder. Okay, so yeah, you will never have to code segment trees from scratch. You just have to change these three functions every time, and you have a working lazy segment tree for anything that you want. Okay, so let's get back to the problem and try to see what's the difference here. So what we notice is that multiplying a number by 10 raised to the power 9 plus 6 and then taking its remainder modulo 10 raised to the power 9 plus 7 is the same as multiplying it by minus 1. Okay, because in the modulo field, 10 raised to the power 9 plus 6 is actually equal to minus 1, right? So multiplying by 10 raised to the power 9 plus 6 is the same as multiplying it by minus 1, because 10 raised to the power 9 plus 6 modulo 10 raised to the power 9 plus 7 is actually equal to minus 1 modulo 10 raised to the power 9 plus 7. Okay, Yeah. So obviously, like, this is a very well-known fact, and like everybody knows this, that n minus 1 is actually equivalent to minus 1 in the modulo field. Okay, so yeah, so essentially what we are doing is, instead of looking it as multiplying by 10 raised to the power 9 plus 6, so if we have a number x, or let's say ai, we can visualize it as multiplying ai by minus 1. Okay, multiplying ai by minus 1. But now since ai has become negative, we can simply add 10 raised to the power 9 plus 7 here, and this is going to be our new remainder. Okay, new remainder. So if the previous remainder at the ith location was ai, and we are trying to multiply it by 10 raised to the power 9 plus 6, it is the same as saying multiplying it by minus 1 and thus simply adding 10 raised to the power 9 plus 7. We don't have to include any modulo here. Okay, notice that's the best part about this. Cool. Right, so let's say we have a range. Okay, so let's say we have a range. Okay, and in this entire range, there was a maximum element, and let's say that this is the index of the maximum element. Okay, and now we are changing every element from x to minus x plus 10 raised to the power 9 plus 7, and we are interested in finding the new maximum. Okay, so it is pretty obvious that this old maximum no longer remains the new maximum. Okay, because we are multiplying it by minus 1 and we are simply adding 10 raised to the power 9 plus 7. So it is very obvious that the new maximum, the index of the new maximum, is actually equal to the index of the old minimum. Okay, because to maximize minus x plus 10 raised to the power 9, we need to have x as small as possible. Okay, right? So if we know the location of the old minimum, then we can get the location of the new maximum. And that's the essence of this solution. So what we'll do is, in our segmentary node, we'll maintain the max value, we'll maintain the min value, we'll maintain the index of the max value, and we'll maintain the index of the min value. Okay, and using these four values, so this essentially denotes the max in the range, the min in the range, the max index in the range, and the min index in the range. So if we maintain these four values, we can very conveniently implement all of these three functions: combine, apply, update, and combine, update. Okay, so let's have a look at my code, and I will explain it to you on the go, and things will be pretty clear. Okay. Right, so basically this is the code for my segment tree. This is my generic all-purpose seg tree template. So yeah, so this is the node which we are maintaining. In the segment tree node, we are maintaining four things: mn, mx, idx mn, and idx mx. Okay, so what we do is, so let's just first look at the combine function. Okay, so obviously answer.mn is going to be minimum of l.mn and r.mn. Similarly, answer.mx is max of l.mx and r.mx. And then we have to give priority to the leftmost indexes, because if there are multiple answers, then we need to output the leftmost one. So if l.mn is less than or equal to r.mn, then the answers idx.mn is going to be l.idx.mn, and otherwise it's going to be r.idx.mn. And we can do the similar thing for mx as well. So we'll just compare the l.mx and r.mx values, and according to that we can actually take care of answer.idx.mx. Okay, so yeah, writing the combine function was that easy. So mn and mx are very obvious, and mn idx and mx idx can also be very easily computed. Okay, so this way we can combine the results of two nodes into a current node. Now let's look at the second thing that we need to take care of. So the second thing is the combine update function. So combine update is very simple. So we are simply maintaining the parity of the number of times we are actually changing a range. Okay, so if we have a new update, we can simply say answer is old update XOR new update, because we are only interested in the parity of the number of times we are multiplying a range by -1. Okay, so combine update function is that simple. And now let's just quickly look at the apply function. Okay, so if update is actually equal to 1, so if update is 0, then that means that the parity of the number of times we are changing it is even, so there will be no change, right? So we can simply return cur. Otherwise, what we need to do is, first thing that we'll do is we'll swap cur.mn and cur.mx, because obviously we've already seen that the index of the minimum and the maximum values are being swapped. So if you can notice here also, we are swapping the indices of the maximum and the minimum elements as well. but we also need to add mod here, right? So we need to multiply them by -1. So cur.mn and cur.mx into equal to -1, and then again cur.mn and cur.mx plus equal to 10 raised to the power 9 plus 7, because the update was x into -1 plus 10 raised to the power 9 plus 7. Okay. So first thing we do is we swap them, and then we multiply them by -1, and then we add 10 raised to the power 9 plus 7, and then we also swap their indices. So this way we can apply the update as well, we can combine the updates, and then we can combine the nodes as well. So this way our segment tree is ready, and now let's just initialize the segment tree. So we initialize the segment tree, and obviously the identity update is going to be equal to 0, because the parity is even initially. We'll just build the segment tree, and then we can answer the queries. We can just take in L and R, we can update the values of the segment tree L and R, and we can pass in a 1 here because we are doing a single update, and then we can output query 1 comma n dot idx mx, because we need to output the index of the maximum element. Okay, so yeah, that's the solution of problem D. Make sure you understand my personal template of generic segment tree, because this code will make sense to you only then. Okay, so yeah, it's definitely a very beneficial thing to understand, because I myself just blindly use this template every single time in every seg tree problem. So it will definitely be very much beneficial to you guys as well. Okay. Alright, so that's all that I had to discuss today. Thank you so much everyone for watching, and I'll see you in the next one.